I'm easy.
Floor is yours.
Okay.
Thank you.
Okay. Evening, everyone. So I've got 2 strikes against me. Those that know me, I'm not a very loud speaker normally, but I've got to speak to this room without amplification. I'm also suffering a bit from hay fever, which makes it even harder. So if my voice starts to run down a bit, do remind me, especially those of you at the back of the room. So, welcome to the second half tonight. This is, we're trying to work it out earlier. I think it's my 3rd time visiting this group. Somebody's nodding. Who's been counting? Thank you. I can't remember what I spoke about before, but every few years I find an excuse to come and visit this group because you're so amazing, of course. So thank you for having me back again. Going to be talking about coroutines tonight, C++ coroutines. Before we get to that, I have another confession to make. So you can see down here, I've got the undo logo. So I've been doing some work with undo recently. I'm actually fully independent now, but undo are actually, they've got such cool tech, I couldn't really help getting involved. So I've been helping them out with a bit of developer advocacy. So when I said I wanted to go and speak in Paris again, they said, well, we'll cover all your costs and everything. Just do like, a demo or something like that. And unfortunately, I didn't get the demo working in time. So I'm not going to do the demo. So I'm just going to spend just a minute to tell you a little bit about undo and why I think it's worth looking into them a bit more. Because they've actually identified this group as being a lot of people working for companies that will be particularly interested in this technology. So it is actually worth looking into if you haven't heard of undo already or already seen what they've done. It's a shame I couldn't show you the demo, which is actually really cool and actually involves debugging Doom in a VM. But you can watch that online anyway, so do go and watch that. Who are undo? So small company based in Cambridge in the UK. They do what we call a time travel debugger. It's the core technology. And it's actually a lot more than that sounds like. We all know what debugging is. You step through your code a line at a time or run to a breakpoint, or when something changes, you examine variables. And really, really useful, an essential part of software development, but also really hard to get right because usually you've got to randomly try to put a breakpoint somewhere you think that might be where the issue is, but it was actually just before then and what actually led to that. And turns out debugging is not just twice as useful, but almost infinitely more useful if you can run backwards instead of forwards. And so that's where the time travel part comes in. And that's why it's a shame I can't show you the demo and actually showing you that in a real code base, particular code base that I'm not familiar with, and I can actually come back and find some really useful, interesting points in time and look at the values there. But that's really what it's about. It's actually recording the run of a process, everything that happens in that process during its entire execution. There's a little bit of overhead, but it's actually usually pretty manageable. And then you can play it forwards, backwards. You can jump to the last time a particular value changed. Not run till the next time it changes, but the last time. So much more useful. Now, knowing the types of organizations many of you work for, you can probably imagine why that would be extremely valuable. So do give it a look, and do feel free to speak to me more afterwards for any more specifics. This is entirely unprepared, so that's as much as I'm going to say for now. Undo.io, go and check them out. That's the marketing part. Worthwhile, I think, but we have now the purely technical material. Back to C++ coroutines. Something I've been interested in for many, many years. Since I used to work in finance, I know many of you do, came across the need for coroutines many, many times. So when it was finally introduced into the standard, or when it was being talked about being introduced into the standard, I was really interested and wanted to see where it was going. And what we got was not quite what a lot of people expected, at least the way you use them, because this is C++, of course. And it wouldn't be C++ if you couldn't take something really useful and then boil it down to the nuts and bolts that you can build anything from. And that's the power that we get with C++ 20 coroutines, but also the complexity, because you have to take those nuts and bolts to build anything. It gets a little bit better with C++ 23 and C++ 26, a little bit more, hopefully. We'll talk a little bit about that. But as of today, if you are using C++ 20 without any external libraries, you've got to build some quite complex machinery yourself. So if you've seen any other coroutines talks before, you'll know that you can work through the talk and you can follow it most of the way through. You get to the end and you think like you've just got to watch the whole thing again or watch another talk, and you still don't quite get it. It's not that complicated. It's a fairly complex solution to a fairly complex problem, but there's just too many things to hold in your head at once. So I've had a couple of runs of this. The first time I did this a few years ago, I took the opposite approach to what I'm going to take today, which is to go for like a really sort of real world problem that sort of matched the complexity of the solution. And I don't think that works for most people. So this is my second run at it, where I'm actually going to start from a position of, let's suspend, if you can pardon the pun, any preconceptions you have about what coroutines actually are and how they work. And let's find out what they are and actually use the compiler to help us to do that. So rather than it being a case of, oh, I want to do coroutines, what sort of stuff I have to remember? We just want the minimum bits of information that we need, along with what the compiler is going to tell us to actually get us to a working coroutine. That's the main part of this talk, and then we're going to build on that and try to piece it together. So we're going to do a lot of mixing of metaphors in this, and as you can imagine, a lot of AI-generated images. Shameless in that, but don't let that distract you. So here's some mixed metaphors straight away. So we're going to make this a bit of a detective story. That's why I say suspend, what you think you know about coroutines. We're going to try and work it out from the bits of evidence and information that we've been given. And then this is where the title comes from. Deus ex machina. I believe that the Latin is pronounced. So gods from the machine. You're probably familiar with this expression. So from the old Greek tragedies or the Greek plays in general, often a complex plot was resolved by some god being lowered in by a crane at the last minute. Something completely outside of what you were watching up until that point. And the word crane and machine actually have the same derivation. So gods from the machine or gods from lowered in from the crane, same thing. We've got the Latinized version. Perhaps it's closer to the French. I'm not sure, but that's the metaphor. So we want to minimize the number of these bits of outside information that we have to sort of drop in on you. There are a few, especially up at first, but we're going to call them out, keep them to a minimum. And then the final metaphor I'm going to use is TDD, test-driven development. So I do talks and workshops on TDD. You may know I have a test framework, Catch, now Catch 2. I sort of built that on top of. And I like to use this test-driven approach to a lot of things. And it turns out that you can do that with this. We're not going to be writing tests, not in the classical sense, but we're going to use that same approach. We're going to write code and see what it does and then make it work. That's the TDD approach. Until we get to a minimum viable coroutine. So this is going to involve a lot of live coding, which is why I've only had a small bit, and I will have more afterwards. Hopefully, it's all going to stay on track. But I've got extra notes on this machine, and that's why we've got the desk out here, so I can be seated most of the time. It's going to make this a bit easier. So I should also point out, we're going to be looking at a lot of code, and looking at code on a small screen that's far away, you have to make it quite big, so to try and reduce the size of it, I'm going to skip some sort of best practice, like I'm not going to show lots of const expras and consts and all of those extra keywords that we should be putting in. If you think they should be there, they probably should. I'll call out some of them that we do need to worry about, but just to excuse that. And, minimal encapsulation, that sort of thing. So, let's get some help from these gods then and actually start out with our first demo. So I'm going to switch to this view. So it's all going to be in Compiler Explorer. The main reason is because I prepared this material for a workshop. So if you like this material, you can hire me as a trainer. And we do all of these exercises in Compiler Explorer. So you follow along and then you go off and you do the same thing. So it's actually a really great way of doing it. Also means I can show you multiple compilers at once. So we've got GCC at the top, 14.2, I haven't updated it for 15, and Clang 19 at the bottom, haven't updated it for 20. So it's all well out of date. No, it's fine. It does everything we need. So if you can see that, can people at the back read this? See some nods and some tentative thumbs up. That's good. Okay. Let me know if I do need to make it bigger. So there's no coroutines here. Literally just a hello world. So I'm going to start off. So we're not even going to talk about what coroutines are, but let's just talk about functions. So here's a function. This is the least interesting function, I think. Does nothing, returns nothing. There's no side effects. It just is. But you can call it. So it is a minimum viable function. So let's get rid of that now. And yeah, so there's our output, nothing. Exactly what we expected, great. That's a normal function. So I will say a coroutine is a generalization of a normal function. We'll pick that apart a bit more later, I won't say too much up front. What we want to do now is make this into a coroutine. In fact, does anybody know exactly what we need to do to make this into a coroutine? I'll give you a clue, it's one of three things. Yeah?
The yield statement, maybe?
Did you say co-yield? A yield statement, yeah. So, co-yield is the actual keyword, is one possibility. If I put co-yield or co-await or co-return, right, they're the three coroutine keywords, co_. If I put any of those three keywords in here, this is now a coroutine. That's not a working coroutine, as you can see, but it is a coroutine. And that is the only thing that makes it a coroutine. And it's worth emphasizing that, because I can say that, and then you can get distracted, and later you think, oh, it's all to do with the return type. No, it's not. The return type is important, as we're going to see. It's not what makes it a coroutine. Right now we're returning void, but we'll address that. So yeah, we've got a lot to deal with over here. Let's pick this apart. So make that a bit bigger. So what does GCC say? It says, error, coroutines, so it recognises it's a coroutine. Coroutines require a traits template. Cannot find stood coroutine traits. That sounds complicated. Maybe we can find something else. But there's a note. Perhaps hash include coroutine is missing. Okay, that sounds useful. And Clang similarly also talks about coroutine traits, also mentions include coroutine. So let's do that. That seems like a very sensible thing to do. There is a header, coroutine. And who here, for any standard library function that you need to use, remembers which header it comes from? No. This is one of those few cases where it'll actually tell you in the compiler error, both GCC and Clang. That's pretty nice, and that gives you an idea of where we're going with this. All right, that's cleared up a lot. Right, now it says unable to find the promise type for this coroutine. Well, what's that? We're trying to work this out. Maybe you've got an idea. Scrap that. It might be wrong. Error, this function cannot be a coroutine. So coroutine trait says that again. Specialized on void, has no member named promise underscore type. That's a little bit more specific. Okay, we need something called promise underscore type. So I'm going to have to introduce the first deus ex machina and tell you that we need a type that is spelt promise underscore type, as the message says, so that part we can work out. But to find it, well, we can do something with the coroutine traits, but that's a little bit complex. We're going to put that aside. By default, the default specialization will look for it in whatever type you return here. So we return something I'm just going to call task. I've just chosen that name at random. In fact, we could call it, let's call it task2, just to prove that there's nothing special about this name. So what we're returning from here, inside there, is a type called promise underscore type. That's what the compiler is telling us to do. We don't know why yet, but hopefully we're going to work this out. And I'm going to take that 2 off, it's a bit distracting, but you get the point. Okay, now where's this got us to? So now GCC is overwhelming us up here. And this is part of that problem of getting to know coroutines to begin with. There's a lot you have to know straight off, and this is GCC's model. So let's set that aside and look at what Clang is giving us instead. A little bit less. We've got two errors. No member named initial suspend. And again, it gives us the correct spelling, so that's useful. And also no member named return underscore void. That seems like the simpler one, so let's start there. And it says it should be in task promise type. So the simplest member return void in promise type would look like that. Bingo. Let's get rid of that. Set aside what it actually does for the minute. You might guess, but we've still got that initial suspend, so let's see if we can get rid of that one just as easily. So remember, this is like the TDD approach, just the minimum that it's asking us to do, and it's not quite enough in this case. So now it's saying member reference base type void is not a structure or union. Okay. Call to initial suspend, so that's the void that it's talking about, the one we just put there. Implicitly required by the initial suspend point, blah, blah, blah. Okay. And GCC is telling us the awaitable type void is not a structure. All right. So we clearly want something here instead of this void. So this is where I'm going to have to introduce the second deus ex machina. So there's more up front. We get less as we go through this. But this one we can work out later once we know a little bit more. But usually, initial suspend is going to return either suspend, never. Make it a bit bigger. Or, I'm going to go with this one, suspend always. It can return other things as well. Usually it's one of these two. Of course, we'll actually have to return something there. It's just an empty type. We will actually look at what that is later. But for now, it's just a marker type. This is the trouble with this font size. Okay, that's got past initial suspend. Now we've got final suspend. It sounds very similar. Maybe the same trick will work. So I'm just going to jump straight to it, copy and paste. And now Clang is saying the expression co-await final suspend is required to be non-throwing. Note, must be declared with no except. That's pretty useful. If you've been doing C++ for a few years, you may not recognize the usefulness of these error messages. They're actually pretty good. And that's actually got us past that, okay. All right, no member named get return object. Let's apply our principle again. Actually, I'm going to put this one at the top. What we usually do is we'll see, doesn't actually matter. So minimum possible implementation. And okay, it's gone past there. Now it says promise type is required to declare the member unhandled exception. Now why it says that a different way, I don't know. but it's the same thing. So void unhandled exception. What does that get us? Now, interestingly, we've still got quite a bit down here for claim. Actually, only one error, which we'll look at in a moment. But GCC is actually happy with this, which is quite interesting. I'm not sure that it should be, and I'm not sure whether this is really a grey area or not. There's been some debate on this. I don't know if Lloyd has an opinion. He has a look on his face as if he was going to say, "Oh, that's because." Okay. There has been some discussion over whether that should be allowed. But let's actually pick apart what claim's saying. So, no viable conversion from return type value of type void. So we were returning void from there, so it must be that. To function return type task. Okay. So let's put our detective hats on here now. So we've got this void here being returned from a function called getReturnObject. And it's saying that can't be converted to this task down here, which is the return object of our coroutine function. So I'm going to say it's probably not that big a jump to say what this returns is what actually gets returned down there. Does that make sense? And that is pretty much what it is. So if we say return task there, let's return an empty task, that should make Clang happy, and it does. So that is our minimum viable coroutine. We haven't had to understand lots of details. We've mostly just followed the error messages. And there was just, I think, was it three points I just had to inject some information. Just those 3 things to remember to get to this point. Now this is as useless, maybe even slightly more useless than the minimum viable function was. But it's a starting point, and it's something we can start to reason about and pick at a little bit. So let's do that now. One of the ways that we can look at this, now ironic, given what I said right at the very start of this, talking about undo, debugging. Debugging is actually very old school in coroutines. It's going to be getting better, I think, but right now printf debugging still reigns supreme, I think. So we're going to end up doing lots of things like this. All right, I want to see if we actually go into our coroutine function. And nothing's getting printed. We're calling f down here. But if we look at initial suspend, remember initial suspend, we said suspend always. Okay, initial suspend always probably means we're starting in a suspended state. Let's test that theory. Remember the other value was suspend never. So that does. So the gear's turning, and there we go. We get our f printed. So yes, now we can see what's actually happening here. So that's what I mean. Printf debugging is really useful. So useful that you probably don't want to do it this way too much. It gets very tedious. So I have, let me see if I've got it prepared somewhere. So I've got this this repo that I've got actually all the links for all of the exercises that we're working through, and lots more. It's actually from the workshop. I can give you a link to this later if you like. There's a file in there called scoped logger. It's nothing that complicated. I'm not even going to zoom in on this because it's really bad code. But it's the sort of thing you would expect, something that logs in the constructor and destructor and keeps a static count and does some indentation and all that sort of stuff. But did you know you could do this? Right, so this is a like the raw link in GitHub. If I copy that URL, I can actually include that directly into Compiler Explorer. I see some astonished faces. Let's test this out. That actually now gives us the log f. I'll put that down there. And there you go. We can see we're going in and out of f. So that's interesting because our final suspend said suspend always, but we still actually do get to the end of our coroutine function. So that's useful to know, isn't it? It's quite valuable. Let's put a few more of these log f's in. In fact, I'm going to put them in all of these functions so we can see what's being called when. Oh. And I'm even going to inherit from scoped logger so I can log the promise type itself. So that just means the whole thing is going to be a scoped logger. And now we can see we've got quite a lot of logging going on. We go into main, create a promise type. So that's the first thing that gets created when you call the coroutine. Then get return object is called and returned. Then it calls initial suspend. And then finally, we actually hit the first line in our coroutine function, assuming we haven't started in an initially suspended state. Then we get to return void. We come out of return void, and then we exit our coroutine function. And then we call final suspend. And notice we've gone into promise type, but we haven't come out of promise type. So that's still left dangling somewhere. And it turns out that's what the effect of having suspend always on final suspend was. If we change that to never, you see now it cleans the promise type up. So you might think, looking at that, oh, we should probably return suspend never from final suspend most of the time, because then it just cleans itself up. But actually, as we're going to see, it's the opposite way around. We usually don't want the coroutine to clean itself up, because what we're going to discover is that the task type, we haven't really looked at the task type yet. It's completely empty. But that's going to be our sort of manager type. And that's where we're going to put the responsibility for managing the lifetime of our coroutine. So it's a bit of a deus ex machina for now, but at least we can see the effects of making these little changes. Yes. And just to test a little bit more, see we've got unhandled exception there. What happens if we throw an exception from here? And bing, we come out of F, and then it calls unhandled exception, and then calls final suspend. So really important, especially to begin with, but actually even if you're very experienced with coroutines, to have some sort of good logging library, even if it's a simple one like this thing that I'm doing. Okay. So that's, I think, the end of the first exercise I wanted to look at. Go back to our slides. And let's actually have a look at the deus ex machinas that we went through to get through that, to remind ourselves. The first one, a function is a coroutine if and only if it has one of those three co-underscore keywords in it. Co-yield, co-await, or co-return. We had a co-return, that was enough. We will look at the other two. I'm not sure how far we'll get through co-await, that's the biggest one, but we will definitely look at them all. The second one was initial suspend should usually return one of stood suspend always or stood suspend never. And we've sort of got an idea of what they actually do. And a bit later we'll see why as well. But for now that's enough. And then the third one, final suspend should almost always return stood suspend always. Whereas it sort of feels like we want it to clean itself up, which would imply stood suspend never, but we don't. So I'm going to say right now, just to get on top of that, almost always return suspend always from final suspend. We're going to make that into a catchy acronym a bit later. All right. We might consider these sort of partial deus ex machinas, because once we understand a bit more, we can see why we need to do these things. But just to bootstrap, we do need that information injected from outside. So a couple more partials. We saw that task has this nested type, promise type. There are other ways too to map that. It doesn't have to be that way, but usually that's just the simplest way to do it. And it does mean that, as we're going to see later, we may not see, so I'll say it now. You often get this cyclic dependency between the two things. So type needs to know about promise type, and promise type needs to know about type. So you end up with forward declarations or that sort of thing. It gets a bit messy, but keeping it simple, you can often avoid that. An instance of promise type is created for us. Did you notice that? Nobody ever created a promise type, but we have one. And its lifetime is tied to the coroutine. Let's pick into that a little bit more. And the bit I'm going to show you next, it's not essential for understanding coroutines, but it may help to make some things click. But it's also very much, I'm going to call it out, just for exposition. It's not actually how things happen. It's sort of like an as-if. So we have a coroutine function like this. We've actually got a value here, but basically it's the same as what we had before. So it's the co-return that makes it a coroutine. Task, that was empty, but we're going to be filling that out. What we haven't done yet is actually assign that task to anything. We'll do that next. Now that's the code you write. But then there's some code that effectively gets generated. And as I say, it's not actually this. In fact, this is wrong in very specific ways, but it might help you to reason about this. What you actually wrote as the body of the function actually goes in the block of some other member function, or whatever we're going to call it. A little bit like how lambdas can be sort of transposed into a class with a call operator, but it's more complicated, of course. So it's just our initial block, which in our case is all of it. But if we have multiple suspension points, you're going to have multiple blocks here. The promise type is a member of this outer struct, which we're calling the coroutine frame. So we never see the coroutine frame. We can talk about it in general, but there is no type that we can ever hold called the coroutine frame. Later we'll see how we can get a handle to it. But that has the promise type in there. So once the coroutine frame is created, the promise type is instantiated. Okay, that's where that comes from. And you can see down here, here it is getting created. And you can see it's being created with the new keyword, which implies a heap allocation. One of the sticking points that some people have when they're thinking about using coroutines in a very performance-sensitive or where predictability is a really important piece of code. I can't afford a heap allocation all over the place. I want to do these coroutines very, very fine-grained. So there are some ways to mitigate that, either to have it optimized out by the compiler, which is debatable how far that gets you, but it can be done. You can also take control of the new operator. And it's not direct allocator support, but you can build allocator support on top of it. We won't look at that today, just to let you know it can be done. Come to my workshop if you want to find out more. So you can mitigate the heap allocation, but if you think of there always being a heap allocation here, it will help you to reason about how these things are working. So we've got the frame, and then promise type.getReturnObject is called on the frame to get the return object that actually gets returned. So that's why this co-return here has nothing to do with the return type that's actually returned, because it's all coming from this generated code. So I said this is wrong. Now this is still wrong, but at least it's got a little bit more to it. So turns out there's some other things that happen as well. So once we've got the return object, before we can actually return it, like you saw the ordering of this just now, it calls promise.initialSuspend to see whether it should actually suspend. Now it can't do this. This equals thing here is nonsense, but it's effectively what it's doing. It's saying, should we actually suspend here? And if we shouldn't, suspend never, then we call the initial block. Otherwise we don't, and that's what we saw, wasn't it? When we had suspend always, we didn't see f actually get called. And only then does the return object get returned. And there's more stuff here. There's exceptions that can happen, and lots of little fiddly details. There are people that have written up more fully fledged versions of this. It's not essential to understand. Just this general idea that we're getting all this scaffolding code generated for us, and that's what's being executed. And it's sort of managing a state machine for us that we're not really seeing here. But so maybe a better way is to actually put it into pictures. Because there are some things that the standard provides for us, both the standard library to some extent, and the compiler machinery, what it's generating. And then the things that we have to provide to make it work. So far, the only thing we looked at that the standard provides is the coroutine frame itself, which we never see, but we do know that the promise type that we provide lives as part of that. Its lifetime is tied to it. So because we provide the promise type and its lifetime is tied to the coroutine frame, we can actually do things that are themselves tied to the coroutine frame's lifetime by putting them in the promise type. It's actually really important, it turns out. And then we have the return object. I've been calling it task, which is a slightly more specific name that may get us into trouble at times, but there isn't like a very good generic name. The coroutine return object is often used. Some people call it the future type, but I think that's even more confusing. So don't go there. A couple of other things we have looked at. Suspend always and suspend never. They are provided as part of the standard library. We will look very briefly at those. And I think we will come back and flesh out that picture a little bit more. But let's move on and introduce a couple more deus ex machinas before we move on. So we can control and destroy coroutines through something called a coroutine handle. So he said that we never actually deal directly with the coroutine frame, but we can get a handle to it. Think of it like a pointer, and generally it does hold a pointer internally. But that's how we actually manage it. We'll look at that in a minute. Where do we get it from? We get the coroutine handle from the promise object. And this is where some of this circular dependency comes in, vice versa. So if you have a promise object, and we know we do because we've implemented it, we can get a coroutine handle. And if you have a coroutine handle, and you may be in a case where that's what we have, you can get to the promise type from that. So they've got this circular dependency. May not mean much for the minute, but as we come through the next example, that will become quite important, I think. So let's put that in our picture. The coroutine handle, stood coroutine underscore handle, is provided by the standard library. And that manages the lifetime, or gives you access to the lifetime of the coroutine frame, and by extension, our promise type. Generally, it doesn't have to be this way, but generally, this is all managed by our task type. Said earlier, the lifetime of the whole coroutine is generally managed by the task type. So let's put that in there as well. And let's look at some code that ties all this together and hopefully make a bit more sense. So let's queue up our next example. My voice is already starting to go, so hopefully it will last. And I think we can just carry straight on from here. What we didn't do earlier was this bit. So actually get the task type. Oh yeah. So what we want is a coroutine handle. Now the coroutine handle is a template, and the template type is the promise type. There is a variation on this that we'll look at in a bit, but usually this is what we need. So there's our handle. Yes?
If you don't mind, I didn't really quite get why we need the coroutine handle,
So this whole, with the promise type, although it's defined within task type, we never actually create it. It's created as part of the coroutine frame, which we never touch. What we have is a handle to it. the only way that we can interact with the coroutine, we're going to talk about destroying it, but also suspending and resuming it externally, is via the handle. So unless we get a handle, we won't ever be able to interact with the coroutine. So we can run it once and then it's done.
Okay, it's sort of like our interface,
Yeah, yeah. I like to think of it like a little remote control. You can control your coroutine going around, starting and stopping it. But we've got to get it in the first place.
I thought it was implicit, but no, you have to declare it.
No, we have to. Well, we don't create it. We're going to get it from somewhere.
Okay.
And I actually told you just a moment ago where we get it from. Who remembers where we can get a coroutine handle from?
From the promise.
Who was? Sorry. So the handle comes from the promise type. We have a promise type up here. And in fact, we actually have the point where we're creating our task right here. We are the promise type, so we can just say stood coroutine handle, and we have to spell this all out again. You might think, yeah, you can use a using statement, but then you get into those 4 declarations. So, and in there is a static method called FromPromise. And pass star this to yeah, that's it. Difficult to fit all this on the screen, but hopefully you can see that. So coroutine handle promise type from promise, that's us. And that constructs our task, which means we have now populated our handle. Does that make sense? Yes.
I'm sort of challenging this, but can you call it in the constructor? What happens if you call it in the promise type constructor?
That's the promise type constructor.
Because you do have in this instance, like there's nothing passed in the get return object which you can use to actually construct the handle.
So you can. I'm 95% sure that you can actually call coroutine handle promise type from promise in the constructor. And it will actually give you a handle.
Okay.
But then what can you do with it? You can store it in the promise type, but we already have it anyway. You can't pass it down here yet because the task doesn't get created until get return object is created. Okay. So this is the first point that's actually useful to us.
Okay.
But I believe you can actually refer to it in the constructor. And there is I think it's to do with the coroutine traits thing, or something related to that. We're not going to get onto today. Slightly more advanced thing where we can actually map different signatures to the promise type, and then we do have to use the promise type constructor, and that's where we get the handle from. So that's why that would also be useful. But for this usage, which is what you're going to use 95% of the time, you're going to do it in get return object.
Okay.
And this is almost always what it's going to look like. Okay. In fact, there is a lot of boilerplate in here that's almost never changing. So we will get more helper types in the future. But we've got our handle in our task, which means that right down here in main, we actually now, you can see how we can control the coroutine. So let's experiment with this. So we said earlier that actually we should always return suspend always and final suspend. Yeah? But if we do that, promise type is not destroyed. So let's fix that. It's not destroyed because, actually, yeah, jumping ahead a bit, we need a destructor on the task. I've lost tilde, there it is. And this one's very simple. We can just say handle.destroy. And there we go. Our promise type is destroyed. Well, the coroutine frame is destroyed, and then by extension, that destroys our promise type. So we can destroy handles. it's usually good practice to test it first, because you may have a null handle. Won't in this case, but you may do. Sorry, yes.
Is there a default task
Sorry, Zara.
Is there a default task structure? Is there a default task structure?
I'm having trouble hearing you, sorry.
Is there a default thing?
Oh, default. The
Or
default.
we have to do all this stuff each time we using
Yeah, that's the thing. Right now, certainly as a C++20, to a large extent as a C++23, and to a less extent as a C++26, it's getting better. We have to do all of this ourselves or use third-party libraries, and there are many out there that will do a lot of this boilerplate for us. So yeah, do use those. But if you're going to use third-party code to do this, you probably want to understand what it's doing under the hood anyway. Now the exception to that would be, we should get on to talk about generators in a minute. C++23 has std generator that basically eliminates all of this for specific cases, and that's the thing. This is like a construction kit for coroutines. So you can build different types of coroutines that do different things. They're not all the same. So you need not just one set of defaults, but several different sets of defaults for different types of things. That said, some of this is the same 95% of the time. So you can probably come up with your own, like maybe like a base class or something that does a lot of it. And in fact, for the memory management stuff, in the repo that I mentioned earlier, we're not going to look at it today, but I've got a couple of RAII wrapper types for the handle. So we actually put that on the handle rather than the task. Got a move-only handle and a scoped handle. Maybe we'll talk about that in a minute anyway. Hopefully that answers your question for now. But yeah, you're getting the point. There's a lot of tedious boilerplate that we have to constantly write to make this work. And there are ways to push some of that down into helper classes, templates, base classes, that sort of thing. But we're doing it all by hand for now. All right, so we destroyed our handle. The other thing we can do is we can say suspend always. I spell it right. In initial suspend. So we're going to start in a suspended state. Remember, we saw that before. We never actually go into F. That means that down here, we've got a task returned to us in a suspended state. What we want to be able to do, remember, here's the TDD approach. We want to be able to call something like task.resume. Which we can't because it doesn't exist. But we are the authors of task, so we can write resume, and that can just call handle.resume. If we do that, now you can see our task gets started, runs to the end as before, and everything close. Great. So far, our task class just seems to be directly mapping the handle. You might think, why didn't we just return the handle from the coroutine and just use that? And you could do. But once you get beyond this, that just doesn't really work. It's too low level. The task, or what I'm calling the task here, the coroutine return type, is our chance to put our own interface on the coroutine. So we can map the semantics to the interface, rather than talking in terms of low-level primitives. That's what the handle gives us. And as we're going to see, we can interact with the promise type here as well. Yes?
Would it be possible to run the function twice?
To run the function twice?
Yes.
Yeah, you just call it again.
No, but
you can't go back.
You call the. If you just call resume again, I think nothing will happen.
No.
Is that kind of a reset or something like that? Or?
There's no reset or rewind. Only ever goes forward. But of course, you can call the whole thing again and start from the beginning. But it's an interesting question because I did make the point earlier that behind the scenes, the coroutine machinery is sort of managing a state machine for us. And with a general state machine, you could have backward cycles. You can go into earlier states. And you could actually do that within your coroutine function. But what we're doing, because we haven't really dug into it too much yet, but here's our coroutine function. The aim here is to make our coroutine function look like linear code, but behave in a more asynchronous, branching way. But that implies still always going forwards. That said, we can have loops. And that generally implies co-yield, which we're going to look at in a minute, and generators. So in that sense, yes, but we're not really going back in terms of state. We're still always going forwards. We've just got multiple levels of the dynamic flow at that point. So don't think about that too much. It's going to complicate things. Okay. So we've got task.resume. Now, what we didn't look at is returning something from the coroutine. So I do co-return 42 there. We now say no member named return value. So we had to write return void earlier, which made sense when we weren't returning anything. And you can probably guess that we want one or the other. I think the compiler won't complain if you put both. In fact, let's just test it out. No, it does. That's good, because it'd be undefined behavior if you did. All right, let's put our log f in there. See that being called. There we go, return value, okay. So we've got this value going somewhere. Before we work out where that's going to go, let's point out the signature here. So, okay, return value, the name, we got that from the compiler error, but the value, I'm making an int because that's what we are co-returning down here. But this is a very much a sort of a concept-based, not actually concept, but conceptual interface, in that it's the compiler is emitting calls to these functions, and whatever you write there, if it can be overloaded to match it, it will work. So you can make this a template, you could make this something that could be implicitly converted from an int, all those sorts of things, just like normal functions that you call. That's all that's happening. So if you have that mental model, then you can appreciate the flexibility of what you can do here. And very often it's very useful to put templates for these things. You can also have overload sets. So you can have multiple return values taking different types. So that is a difference to normal return. You can actually have different types and do different things with them. You still have to map them to something at the other end, but that's your problem. So what can we actually do with this return value? Because this is being called on our promise type. We don't have access to the promise type, do we? See some shaking heads.
No, we do from the handle.
Sorry?
We do from the handle, no?
We can get it from the coroutine handle, which we have. So first thing we need to do is store this somewhere. So I'm just going to do the simplest thing to work and say returned value, and I'm going to leave it uninitialized because it's all the rage these days. And if you want to know the horrors of uninitialized variables, just speak to Rick. But we'll let it pass here. In the workshop, I actually did a little exercise. How can we make this safer? But so we're setting our return value there. And what we want to be able to do though is say, so I've also got a macro called log. I should use shorter names. Right, we want to make this work. So again, TDD, write the code we want to use first. So it's going to look something like this. Now this is where we said there is a method on handle, just promise, and then we can say returned value. If I got that right. And there we go. Return value is 42. Wasn't that hard, really? And the secret was just that the promise type is like our staging ground for values going in and out of coroutines. So in this case, coming out through the return type. As we'll see, we can also yield values out here, but we can also get values back into the coroutine. I'm not sure we'll get onto that tonight, but this is where it happens. And it's straightforward. It's just like a couple of extra levels of indirection that we might be used to. Okay. Now, I think I was meant to talk about something else as well here. Okay. Yeah, I will very briefly mention that, as written, we can take copies of our task type. Sorry. Get rid of those. Is that a good idea?
No.
Well, the output tells us, fortunately. And you can probably reason through why we're getting this zigzag. So internally, we've got the coroutine handle, which we're destroying in the destructor. So now we've got two copies of the same coroutine handle, both being destroyed. So double delete, double destroy, effectively. So generally, we would say that we should disable, let's put it here, disable your move constructor. Should make that not compile, great. But then you still got move assignment operators. So Lloyd probably knows where I'm going with this one. You can delete that as well, but it turns out all you actually need to do, make that two, is delete the move assignment operator. And that also deletes the move constructor, but it leaves everything else intact. So that's actually one step ahead. I missed a stage, which is where we should have disabled copy first. That also disables copy. That's what I meant to say. So this is a non-copyable, non-movable type. One line of code, not too bad. You may want to make them movable, in which case you do need to implement your move constructor and move assignment operators. And that's where I say, you probably want to actually have a specialized type that just wraps the coroutine handle to do that. And then you can follow the rule of 0 for your task type. So normal principles apply. Always follow the rule of 0 where you can, and where you can't, follow the rule of 5. That's another talk. But that's a useful check for this. Generally, we only need that sort of scoped task, so that's actually sufficient. Okay, I better make that compile again. Take that line out. And go back to here where we can now draw that line and say, yes, it's the responsibility of our task generally to manage the lifetime and interface of the coroutine handle and the promise type. So we've seen all of those things now. And we've done that. So here's the catchy acronym I mentioned earlier. Easy to remember. Okay, actually it turns out it is more catchy than it sounds. Almost always, suspend always from final suspend. Why? Because if you don't, the coroutine is going to clean itself up. And how would we have got that return value if by the time it had finished, the coroutine had gone, taking with it the promise type? Yeah, so hopefully you can see why we want to keep control of that. We want to be the ones that says, no, now we're done with it. Now you can clean up. So that's why we need to take control of the lifetime management. So almost always, suspend always from final suspend. There are some cases where you don't want to do that, and you will know when you hit them. Generally involve resuming coroutines on separate threads. And there you want it to clean itself up. Otherwise, just follow that rule. Easy to remember. All right, why have I put this back up? Oh yeah. Come over here. It's because we already did that one. Yeah. Out of order execution, don't worry. Nothing to see here. So I think we've got time to cover co-yield. So the second of our three co_underscore keywords, we've only looked at co-return so far, the least interesting one. But we covered a lot of ground, I think. I think we're a good place to move forwards. So let's go straight into another exercise, of course. And we can carry straight on here. But instead of co-return, let's keep the co-return in actually. And we'll just add the co-yield. So, following the compile errors again, no member name to yield value. Starting to see the pattern now. So, let's add, no, not return, yield value. And it's probably going to take the value. Surely that's going to work. Nope. But it just does tell us what's wrong. So base type void is not a structure or union again. Okay. So I do need, again, to just inject another deus ex machina here. Yield value has a return type, and it is whether this coroutine should suspend or not. So the same as initial suspend and final suspend, it's usually going to be suspend always.
So it's almost always suspend always everywhere.
Yep. I need to actually return that. Right. There we go. So, when we hit the co-yield, coroutine machinery calls yield value, passes it that value and says, do you actually want to suspend? And you're going to say, yes, of course, that's why I wrote the co-yield there. So that's why it's usually going to be suspend always. But you do have control. Sometimes you might say, well, yeah, I know you gave me this value, but yeah, nobody needs that. We can just carry on. And we'll look in a minute about the relative overhead of these different decisions that we can make. It's another point of control you have that you really need. So almost always, suspend always from yield value as well. Okay, but other than that, it looks very much like return value. Yes?
So seeing that on yield value, we provide a suspend condition. So why you decide on return value to provide a suspend condition instead of the final suspend?
I think I missed the last part of that.
So instead of having a separate function final suspend, why would we return the suspend type on return value?
Oh, I see. I think if you we look down here, is it going to show us? No, because we're suspended. Let me get rid of that yield for a minute. because return value gets called here. Then we actually exit our coroutine function. And then we call final suspend once our function is already completed. So if we did it up there, we could do it, we'd have to hold on to it and then decide what to do, and it's just a bit awkward. They're just different points in time, different decision points. Maybe the design could have been different. You can say that about a lot of this. But it's not that terrible in this particular case. Yeah.
Just to go back about return value. Okay, we are talking about simple type. And if return value, it will be more complicated. I mean, struct or class. Is it the same way to generate it, not memory leak a lot, or how it can be?
So it's a good question, and the answers are in everything I've already told you. But that's the nature of this. There's this moment where all these things sort of overlap in your head, and you think, now I understand coroutines, as if you just like woken up out of the matrix. And it really comes down to realizing that the promise type is a member of the coroutine frame. So all the time the coroutine is alive, which is the same as all the time the coroutine function is running or runnable, which is the same as the lifetime of the handle that you've got in the task type. These are all the same thing, like the Steve Jobs thing. They're not three separate things. Then we know very definitely what the lifetime of this thing that we're putting these values into is. And we can reason about that. So we can say, like if we have our handle in the task, we are managing that lifetime. So until the end of the task, it should be safe to call into the promise type and get values out of it. We know they're still going to be there because we are managing it. But yeah, there's so many different layers to this, you can lose track of that. But once that becomes sort of well ground in, then you actually start maybe getting really dangerous with this stuff. And can have like references to temporaries, knowing that that temporary is still alive when you're doing this thing. And you can go a bit too far, but it is actually quite flexible. But it's a good question, because it really gets to the heart of that. Thank you. All right. We do need to make this yield value work. Let's put the co-yield back in. In fact, we've got our yield value here. We can store it in exactly the same way, directly in our promise type. Where are we? Losing track. You throw about all these one-line functions. I did say I'm going to try and reduce the amount of scrolling, but then we have to scroll from side to side instead, so it doesn't always help. And then, as well as get return value, we can get yielded value. In practice, by the way, you'll almost never have a co-return and a co-yield in the same function. So you won't have both of these sort of things. Did I get that wrong somewhere? Nope, just catching up. Okay. So I've just doubled everything up, as well as the return values, we've got yielded values. And you can see down here, well, we've got the yielded value, the 1, but our returned value is now 0. Anybody know why?
Because it's suspended.
Suspended, yes. I think you're all saying the same thing. Yeah, so we suspended again. So co-yield is the suspension point. We talked about that with the suspend always. And now we have the means to resume again. So let's put that in. And gone off the screen. There we are, got our 42 back. So we know we got to the end. Great. But unlike co-return, of course, we can have multiple co-yields. In fact, let's see where this goes. Recognize the sequence, I'm sure, but Of course, now we've got to have corresponding number of resumes on the other end, and it starts to get a bit tedious. We probably want to write some sort of loop here. If we have a loop, then we need to know when it finishes. So resume just returns void, but we could give it a Boolean return. And there's a member of handle done that tells us whether the coroutine is completed or not. So handle.done, resume will return true when the coroutine is finished. Now, I always get this wrong, so let's see if I get this the right way now, because I'm out of sync with my notes, so can't trust them. I think that might be it. Nope. Oh, was all finished? Didn't get any of them. Ah, did not. That's more like it. It's a whole Fibonacci sequence, and we finished with 42. How about that? That's the right answer. Yes?
Sorry, what is the return type of any the value of task.resume? Like, is it
Sorry.
going to
Had a
oh, I'm sorry.
blocked here this week.
Like,
So.
what is the return type of a task point resume? The return type or the value? Because we are currently checking if it's not equal to 0 on the while loop. But what is actually inside it? Is it a boolean or something?
So dot done.
Oh, it's only a boolean.
Yeah. Good question. Thank you. Let me go back to that. So yeah, we're just returning handle.done. So that's just a Boolean that says whether the coroutine has completed or not. All right, so I managed to get my loop to work. We could, of course, write this in a loop as well. Maybe I will in a minute. Or maybe not. No, I think I will. Let me, I'm going to copy from here, just so I get this right. If I can find it. Oh, here we go. Right. I'm not going to talk this through. It's just a Fibonacci algorithm. But I will use stud exchange. Very underrated little utility. If you're not using stud exchange whenever you can, you're doing it wrong. Get rid of the co-return now. And I'm doing it wrong because I need to include utility. Okay. Now, of course, it never actually completes. But we've got a loop on both sides. So let's I'm gonna come back to that in a second. I'm gonna come back to the slides and just talk about what we've done here for a minute. We've got our co-yields. I've written them out like this here, but you could do it in a loop, as we said. So when you do co-yield, that invokes yield value, as we saw, and we should return suspend always. And returning suspend always causes us to actually drop out back to the caller with our loop, where we can get the value out that we stored. This is just what we wrote a moment ago. Get that from the promise type. And then we call .resume again, which goes back into the coroutine function to the next yield statement, and so on until we get to the end. So you don't usually have the co-return there. And this is actually part of the inspiration for the picture on the opening slide. I didn't really talk about that, but obviously you recognise the original piece of art that is very subtly hidden in this AI-generated version. But had this sort of idea of these sort of, swirls of code execution. And you can sort of see that going on there. And I think it's appropriate that that image was produced by generative AI. For reasons we'll talk about in a second, but I thought I'd just see if I could take it a bit further. I said, produce a painting in the style of Van Gogh's Starry Night, but depicting a binary pulsar. Came up with this, which I think is actually an even better fit. So how about that? So there's our co-yields. There's our calling code. And so generative AI has given us generators. So slightly extended pun, but hopefully you get the idea. So that's the pattern. Coroutine code, you have some sort of loop with co-yields. Can be an unrolled loop, potentially. Client code, loop until done, we get value, we resume. There's nothing really special about that pattern. That's just loops, or iterators, or ranges. And in fact, if we've got those three things, we should be able to map them onto iterators and ranges. And if you've done that, then actually there's nothing really left usually about our coroutine return object or promise type that's actually specific to anything else other than this pattern and the type we're operating on. So it's the perfect thing to generalize to what C++23 has finally given us with std generator. So let's see what that looks like if we use std generator. And have I got? Yeah. Okay, do it manually. So we need C++23, and we need to include generator. Actually, not going to need our logging because we're going to get rid of all of the task type and the promise type, and we're going to return std generator of int. And instead of a while loop, we can just say for make it I in task, which won't work for reasons we'll look at in a second. Oh, I don't need the logging. Do it this way. All right. And yep, it's not declared in scope.
Line 16, you're missing a bracket.
Sorry?
Line 16, you're missing an opening bracket.
Line 16. I haven't got onto that bit yet.
No, open brackets for the
Curly
for loop.
brackets.
For the for loop. The open bracket.
Ah, I see.
For loop. Yeah.
Thank you.
That's one thing. That's one thing.
Okay, yeah, that's still. Ah, is it because? Tell you what, let me go to the one I prepared earlier. So I think this only works with certain compilers at the moment. Yeah. Okay, so it was Clang, not GCC. I closed the wrong one. Okay, let's look at what we got then. So just included generator, std generator of int, do our co-yields, and when I'm calling it task, it's the wrong name at this point. Task is a different thing to a generator, but we can take, in fact, we're not even using that one, that's erroneous. We can take what our coroutine is generating, pass it off to views take, just take the first 10. And then we've got our first 10 Fibonacci numbers. And of course I can change that now to whatever I want. And it's nicely composable. Sometimes ranges actually works. There we go. Where it doesn't work, as you might expect, and that's what this code was originally trying to do, is like this. So there's one thing to be aware of. What you pass to std views take has to be an R-value reference. There you go. So if you call the function directly, then it works. Otherwise, you're going to have to use std move. I'm not even sure why that is in this case, but I think there's good reason for it. But just something to be aware of if you're using generators. That's not really to do with generators, that's to do with ranges. But the generator part is exactly as it should be. That's it. Co-yield. Done. And it's a generator return type. How it should be. So everything we've done up until this point has now been put into the standard library. Well, for co-yield. All the rest of it we don't have yet. So you still need to know everything we've talked about so far. And we're getting quite late. I just want to very briefly introduce you to co-await. We're not going to be able to get into it too much, but I can bring the slides back up. Okay. I think there's a little interlude in the middle, so it's probably a good time to run towards the end anyway. So just to remind ourselves, one of those three keywords makes it a coroutine. We have to define the promise type. This is usually the first thing you see when you start looking at coroutines. You've got to understand all of this. And I think we pretty much do at this point. The return object, that's what actually returns the value from the coroutine function. Usually has a handle that we can get from the promise and wrap it in your own type. Initial suspend just says whether it starts in an initially suspended state or not. So it can be suspend always or suspend never. Final suspend, almost always return suspend always for final suspend. Almost always. Unhandled exception, most examples will just say std abort, but obviously you can put proper handling there. You don't actually get past an exception pointer, but you can call std current exception to get the one that's currently in flight if you need to store it for later retrieval, but we'll leave that as an exercise. Yield value, as I said, it can be a template, or it can be an overload set, or just something very specific, but otherwise very similar to return value. If you use co-yield. Co-return, we did see that you use one of return void or return value for obvious reasons. I did say that you can actually have an overload set for return value or a template. You can actually return different types, which is really weird. But there is a bit of a foot gun here as well. If you don't put either of these, if you have a co-return, the compiler will warn you, usually. If you don't, and you run off the end, it's like running off the end of a normal function without a return, you get an implicit return. we get an implicit return void if you run off the end of a coroutine. You don't get the compiler warning, which is interesting. And it's undefined behavior. So a little bit of a foot gun. The reason, by the way, we just saw generators. They generally don't return. So you don't actually want to have a return void because you're not actually expecting to ever finish. But it does leave this bit of a area of UB. Yes?
Is there a reason? It is not just informate?
Sorry?
It is a defined behavior, why not informate program?
I don't know what happens in practice. I mean, you can try it, and I don't think anything much happens. You just sort of get away with it. But bad things could happen. And maybe they've addressed it in C++ 26. I haven't heard, but you puzzled? Do you have any? No. Yeah. As far as I know, it's just classed as UB, and that could potentially mean anything, including it just behaving innocuously. But just try to always put it there unless you're writing a generator. One thing to be aware of. All right. The coroutine interface type was the other name, or return object. Well, we started off calling it a task. Then we saw it could be a generator. It's a different type of thing. But it could actually be anything. We said it could even be a handle or some other existing type. Like people have mapped them onto stood optional, stood expected, stood future, all sorts of things. And you can do that because you've got these extra levers you can pull with specializing some standard types, like we saw coroutine traits. Lets you do that. We're not going to get into that today. Just be aware that you can do that. So very, very flexible. You have to impart the semantics that you want to your coroutines, or pick the library that's going to do it for you, is the trick here. Yeah, I'm only saying this again just to say that there was one more to look at, which is co-await, which you're not really going to have time to dig into. But I want to just address one thing, which is the difference between an awaiter and an awaitable. What is the difference between an awaiter and an awaitable? So the first answer to this, it doesn't really matter. It's like, what's the difference between a parameter and a function argument? There is a difference. You should probably know it. It doesn't really matter if you get it wrong. What's more important is to know that there is a difference, not which is which. So an awaiter is something which has a specific interface, much like the promise type, something that's defined by the coroutine machinery. It's 3 functions. We'll very, very briefly look at them in a second. An awaitable is something that you are able to await. So you can put co-await in front of it, and ultimately that's got to map to an awaiter, but it doesn't have to be that type. So you can make anything an awaitable, the same way that you can make anything a coroutine return type. So awaitables are things you can co-await on. They must ultimately give you an awaiter that the coroutine machinery can call. Okay, we'll have to really, really speed up. Trivially awaitable types are actually awaiters that are trivial in the sense that they only differ based on whether they make the awaiter suspend or not. And there's 2 of them, and they're called stood suspend always and stood suspend never. Those are the trivially awaitable types. If you're in an IDE, you just click through to the definition in the standard library, and you can see, yes, they are actually trivial. No implementations except a return true and a return false. But it's really useful to have them in the standard library, because then coroutine machinery can look at the type and say, oh, I know what that does at compile time, or const expr, of course, and potentially not even generate code for it. So that's as much as I'll say there. But I did say I would show you the interface. So await ready is the one that does the work in the trivially awaitable types and is almost never used beyond that. That just says, like with the yield value, do you actually want to suspend here where you said to await something? Because it may be you say, I'll wait this thing to happen. And you get into here and it says, that's already happened. Don't do anything. I've got it, I'm ready. So you can do that here. assuming you say force, so suspend, then it suspends the coroutine and calls the weight suspend, gives you a coroutine handle. This specialization it's actually a void, so empty angle brackets, is a type erased variant. So you don't actually get access to the promise type, but other than that, you've got access to destroying and resuming and stuff like that. So it can be really useful. And when the caller resumes a coroutine, it calls a wait resume. And it's got void there, that's wrong. Well, not wrong, but it's not complete. If your co-await expression returns something, it comes from here. But we're not going to have time to get into that. So over time, but this is the flow. So when you co-await something, it calls a wait ready. If you say true, it has to call a wait resume because that's got the return value and comes straight back in again. Otherwise, it suspends the whole coroutine, so that's got a little bit more overhead. That's why we want to avoid it if we can. And then calls, is it going to come? Here we go. Await suspend, which is actually much more complex and it's got a few different return types we're not going to get into. But you can short circuit again or return control to the caller. And the final one actually lets you suspend another coroutine. That's all we're going to have time, I think, to get into. So I'm going to, skip ahead. And just say one final thing about our waiters, because didn't get a chance to dig into the semantics, but one thing that's worth noting about our waiters is you can do everything that you can do with co-yield and co-return with co-await. Might be a little bit more code, but it's the more powerful of the three. You can do everything with co-await. Co-yield and co-return are just like specialized versions for specific cases. So definitely worth digging into that more, but that would be another hour and a half. So we'll finish there. Thank you very much.